During the PhD, she stayed 3 months here in our lab during the PhD under the supervision of Professor Ivo. So it's a pleasure to have you here again. She had several postdoctoral and research collaborations in different institutions, including Centre de Recherche Scientifique et Technique and Analysis Physico-Chimiques, Algeria, Institute of Scientific and Industrial Research, Japan, and University of Bologna, Italy. She also won several awards and grants. The last one was Africa Research Initiative for Scientific Excellence Fellowship funded by the European Commission through the Africa Academy of Science in 2022. Is affiliated to the African Academy of Sciences, Africa Science Leadership, Organization for Women in Science for the Developing World, among others. Her research interests are focused on nanomaterials, nanotechnology, and renewable energy systems, photocatalysts, chemical sensors, and solar cells. Please welcome Bridget, and you have the word now. Okay.
Thank you very much, Professor Sebena. Am I visible here?
Yeah, sorry.
Am I visible here?
Yeah.
Or should I go up here? Good afternoon once again. It's a pleasure. I'm pleased to be here. It's a great privilege. My talk today will be on hollow nanostructures for carbon monoxide and ammonia sensors. And these have been made possible because of the CAPE Spring program, together in collaboration with Professor Jose Sebena. Before I go further, I think it's good for me to orient you where I come from. I come from Quênia, which is in the East African region in Africa. And as you can see, the equator passes right through Quênia, so the temperatures are high throughout the year, except for a couple of times that we experience the rains. And my university is called the University of Nairobi. It's within the city center, which is Nairobi, the capital city of Kenya. Now, there are several things people can do in Kenya before I start. We are well known for the safari, and it's the only country where the national park is in the capital city. So you can have your breakfast with giraffes and lions. And also it has the Masai Mara, where there's a wildebeest migration every year. It's a beautiful scenery. And not to mention Mount Kenya and the famous Maasai people with the rich culture. So you're welcome to Kenya. I hope that one day I'll welcome some of you in Kenya. Now to my talk. My area of focus looks into basic needs for children, specifically Africa. That is things that address clean water and sanitation, as well as healthcare. So my research focuses on good health and well-being. It focuses on addressing sustainable development goal of clean water and sanitation, affordable and clean energy, as well as sustainable cities and communities. So my research interest, just to overlay what I focus on at the moment, as I'm an independent researcher. Once I finish my PhD, I'm looking more into the chemical sensors and the photocatalysis, basically looking into nanomaterials, a wide range of nanomaterials which I've synthesized in the last 7 years, including hollow carbons, core-shell nanostructures, as well as nanodots, all these for application in monitoring environmental pollutants. So I'm interested in hollow nanostructures because of their properties, such as the tunable surface areas, the strong surface interactions, and the ability to modify the surfaces, either inside or outside, for allowing for adsorption of ions. To start with, I'll share my work on the use of hollow carbon spheres for ammonia sensors. Now, hollow carbon spheres fall under the category of zero-dimensional carbon nanomaterials, which are spherical materials. And they are divided into two. We have the core shell approach, whereby you can have the core of the shell being a metal oxide, a polymer, or carbon, or even a semiconducting nanocrystal. And then we have the hollow carbon spheres, meaning that the inside is empty and the shell is made up of carbon. These materials are synthesized using a wide range of techniques, but the common way of obtaining hollow carbon spheres is what we call the templating method. In these, you take a template such as silica, polystyrene, or surfactant. You coat the carbon over it, and then you remove the template to get the hollow sphere. This can be done through top-down or bottom-up methods. And the commonly used method is the chemical vapor deposition, because you're able to control the surface properties, as well as you can use readily available precursors, and also be able to modify the final shape of the product. Now, hollow carbon spheres have been applied in various ways, such as in energy storage, supercapacitors, in fuel cells, in lithium-ion batteries, and also as catalyst support. Up until 2016, there was no work on the use of hollow carbons in sensors. So that's what motivated me to try and see if they are applicable in sensors. Now, a sensor is a device that receives a stimulus and it responds with an analytical signal. So the stimulus can be mechanical, thermal, optical, or chemical, and the response can be either change in voltage, current, or charge, with the principle being either capacitance, resistance, conductance, and so forth. And chemical sensors, therefore, we are looking at transforming a chemical information to a useful analytical signal. So if you have an analyte, and this is your sensor and sample interface, you expose your analyte to the sensor, which is coated with a sample. Then you can have interactions taking place, adsorption, or electron donation or electron acceptance, which leads to change in the conductance. So this is a sensor without the exposure to analyte, with exposure to analyte, and after the desorption taking place. From this, you can be able to get the sensor response, which is the change in the conductance over the base conductance. Or if you do this over a range of concentrations, you're able to get a slope that can give you the sensitivity. So ammonia sensors are very important, specifically because ammonia is a toxic compound, not only to mankind, but also to the environment. And high ammonia concentrations, owing to the use of nitrogen-containing fertilizers, result in soil acidification, results in reaction of ammonia with nitrogen-containing compounds to make particulate matter, and this particulate matter then leads to smoke or blood visibility. Therefore, it is important to monitor ammonia so that you can control these environmental pollutants. So ammonia sensors have been used in monitoring meat spoilage. They have been used also in the medical field to monitor the breath of patients, kidney patients, and also in agriculture for poultry houses to monitor how clean these poultry houses are. However, when it comes to sensing of ammonia, the environment plays a key role. That is humidity and temperature. So it is important then to know how to control the humidity and temperature for these sensors. So the objective of this work were to generate hollow carbon spheres, to investigate their morphology and structural properties, to determine the effect of annealing the hollow carbons on the physical chemical properties as well as the sensor behavior, and also to explore the properties of just hollow carbon and hollow carbon with a polymer composite for ammonia both in ambient and humid environments. So to achieve this, we obtained the silica using the common stopper method. So the silica is solid, then coated the carbon in a reactor whereby toluene was the carbon source, and the silica is here. The reaction conditions were as shown here, and then after that we etch away the silica to get the pristine hollow carbons. To check the effect of annealing, the pristine was heated up in air at 300 degrees Celsius to get the annealed hollow carbons. So for the sensor fabrication, we used the surfactant assistant dispersion method, whereby the hollow carbons were mixed with the surfactant. and then ultrasonicated and drop casted. For the polymer composite, the same was done, and the sample drop casted to form the electrode. So the ammonia sensing was determined by varying the concentration between 74 ppm and 295 ppm, and the relative humidity was measured at ambient. At that time, it was very humid. It was during winter, 50%, and under a controlled relative humidity condition between 10 and 97%. So the first thing we looked into was the response as a function of frequency, whereby the frequency was varied between 0.1 and 150 kilohertz. And from these, we wanted to determine the frequency at which there is the lowest signal to noise, the higher signal to noise ratio, or the signal to noise ratio was low. So in this case, we obtained 1 kilohertz, whereby we could be able to see there is no noise, there is less noise in this particular position, and therefore we use 1 kilohertz for the rest of the measurements. And we did the ammonia response at ambient condition, which was 50%. The room temperature was 20, and for the pristine, you can see here the response. It takes a very long time to respond, over 2,000 seconds. And even the polymer and the anneal, they take longer to respond under ambient conditions. With a two-step saturation, this is because of the slow adsorption due to the presence of defect on the surface. So then we increase the temperature to 40, and you can see the drastic decrease in the response time and recovery time. Ideally, you want a sensor that responds quickly and also recovers quickly. However, while doing this measurement, we noticed that whenever humidity changed, the measurements changed. So the data was really not very much reliable. And therefore, we decided to look into now the relative humidity response instead of ammonia. So what we did, we created humidity levels between 10% and 97%, and we then measured the response of these devices at the various relative humidity. And as you can see with the pristine holocarbons, it showed a very high response to humidity as compared to the polymer and the anneals, which is the data is computed here. For the composite, above 59% relative humidity, there's a decrease in the response. This is because the polymer plasticizes, it swells above 60% relative humidity, and therefore bars the water molecules from reaching the electrode surface, and therefore this resulted in this. For the anneal, there was a drastic decrease in the response towards relative humidity. This is because annealing removed the surface functional groups, and also it removed the presence of amorphous domains. So looking into the relative humidity sensor behavior, we see that if we compare these works together with other works in literature, we see that this material, pristine holocarbon, exhibited a very high relative humidity response. That tells us that while we were doing ammonia, actually the sample was responding more to the humidity than to the ammonia. So once we determine this, then we ask ourselves, can we be able to determine the ammonia? Can we detect ammonia in the different relative humidities? So we did, we controlled the relative humidity of the environment, and then we try to detect ammonia, and you can see here for the pristine, it does very, very poorly. And also the annealed also does poorly. However, the polymer gives us a 7% sensitivity. So the same was done for all the other relative humidities to see whether we can detect ammonia in a humid environment. And this data here shows this is the ambient condition. This data here shows the pristine comparison of the sensitivities towards ammonia. And you can see for the pristine above 75%, we're not able to detect ammonia. Why? Because the surface is already oversaturated with the hydroxide ions. And for the polymer at 59% relative humidity, we still obtain very low sensitivity of ammonia. However, for the annealed, it was possible to detect ammonia in all the humidity ranges. That is by just varying the surface groups and their amorphous domains and the structural property, we are able to sense ammonia in a humid environment. If we compare these with other data in literature, you see that most people in literature, unfortunately, they don't do sensitivity. I don't know why. They always report percentage response, and therefore we had to recalculate our data to fit literature, which is through by looking at conductance, change in response times 100, and also resistance, the change in response times 100. And our samples exhibited higher response towards ammonia than others recorded in literature. So that means that if we just compare the pristine and the anneals, the heat treatment does change a lot the surface features, allowing for better sensitivity. So looking into the mechanism for sensing, these are hollow carbon spheres. They are not very electrically conductive. So the question was, where is the mechanism for this material? Because it's not electrically conductive. And after a series of discussions, we came up with the sensing mechanism, which is the pore filling mechanism, because it's a porous structure with pores on the shell, and the pore, the empty hollow sphere. We considered a hollow pore filling in that if it's water, when water gets into the pores or adsorbs onto the pores, water has got higher electronic conductivity than air, and therefore the lone pair of electron in the water will interact with the carbon, creating a dipole charge, further leading to an increase in conductance. And at very high relative humidities, because of the high dipole moment of water, you then have proton hopping taking place, and therefore you experience very high conductance. On the case of ammonia, the same principle applies. Ammonia is more conductive than air, and therefore when ammonia molecules get into the pores, they are able to create a dipole charge, further leading to a change in conductance, which is way different from the mechanism for carbon nanotubes and graphene, which are highly sp2 hybridized. During that time, there was a student of Professor Ivo, Dr. Rafael, was doing mathematical and programming things. I can attest that I'm not very good in this. Yeah, so, but what he did was he would take the response of the three sensors that show a linear response towards a specific concentration of the analyte, and then created a tool that is able to give a magnitude of response using angular coordinates. And at different humidities, you're able to get the different sensitivities. Once you have that, then you can look into the concentration using another 3D map to determine the exact concentration of a material. And through this tool, we were able to get 4 clusters. The relative humidity, we were able to get 4 clusters for the sensitivity regions. That is the 10%, the 33%, and 97%. However, in between 59 and 79, there was overlap, meaning that now with these kind of sensors, it was not possible to differentiate that kind of data. And as Professor Ivo would say, you either detect the ammonia in very cold places, very low humidity, or very high humidity, right in the ocean. Anyway, so in conclusion, I can say that the ammonia sensing properties of the hollow carbons was found to be humidity dependent, and the presence of structural defects and hydroxyl groups plays a critical role in varying the humidity response. The most important thing is by annealing, you're able to decrease the relative humidity dependence, with the pristine giving you a higher relative humidity response and the anneal giving you a higher ammonia sensitivity. And we are able to simultaneously identify relative humidity and ammonia concentration in 4 different regions using the tri-stimulus analysis. And these responses were higher than those reported in literature. So this was the first work on hollow carbon, and it was really amazing. And through that collaboration, we were able to published the work, which was a hot paper collection in 2017. And after that, we also collaborated to look into doping of holocarbon spheres for detection of volatile organic compounds. And we obtained that by just doping the holocarbons, we are able to decrease the detection limit towards ammonia, towards toluene, and also lactic acid. So this is work that we've done on holocarbons so far. And with the structure of holo, I got excited. Can we use the same principle for metal oxide? So that brought me to the other approach of using holo-tin for oxide for the detection of carbon monoxide. This is a very difficult thing to do because we know carbon monoxide, you need high temperatures. But I wanted to see whether it is possible. So tin for oxide has good properties, excellent electronic conductivity, and tunable catalytic and optoelectric capabilities. And therefore, it has been researched a lot in gases. And the holo tin oxide nanostructure is very interesting because you're able to adjust the diameter, the thickness, as well as the porosity. However, majority of the work is done on high temperatures, above 300 degrees Celsius. And with the recent progress in Internet of Things, artificial intelligence, and micro-mechanical systems, there is still a need to make room temperature sensors. Because when you think about the applicability, for example, in Africa, we have little resources, so we have to think of solutions that require little resources. So to achieve high sensor responses, there are various approaches that people have used in literature. One of them has been to use the additives, metal additives onto the tin for oxide to increase the oxygen vacancies and also the surface catalytic activity. Also quantum confinement, making the particles very, very small so that you can tune the structural properties, tuning the microstructure and porosity. And the last one is the light-induced sensitization. Now, looking into the microstructure and porosity and quantum confinement, can we use the templating approach to use a core shell polar structure to lead to increased number of active sites and perhaps detect carbon monoxide at room temperature? So the objective of this specific work was to explore the morphological features, structural and textural properties of the holo tin oxide synthesized from core shell silica to determine the holo tin oxide sensor response towards carbon monoxide at ambient conditions. So to achieve this, we synthesize holo tin oxide sphere. Instead of using a solid silica, we use a core shell silica. That means the core is solid, the shell is mesoporous. This was then mixed with sodium cyanide solution, hydrothermally treated, and then washed to form the silica at tin oxide, and finally etching away to get holo tin oxide. So for comparison purposes, we did the same, but without using the template to get template-free tin oxide under the same conditions. So looking at the morphological features, this is the core shell silica. Unfortunately, we didn't manage to make very small silicas. We only managed to make around 638, I think because of the centrifuge we were using. It was not a high-speed centrifuge, therefore it couldn't sort our spheres the way we wanted. And then this is the core shell, as you can see here. Inside it's solid, outside it's a little bit, it's not so black, it's a little bit gray, meaning that it's a shell, which is mesoporous. And from there we coated and removed the silica to get these holo tin oxide spheres. And for the template-free tin oxide, we got agglomerated particles, which were way much smaller than the one made using the template. Looking into their structural features, we did powder X-ray diffraction. This is for the core shell silica. This is for coating, after coating with tin oxide. And you can see once you coat with tin oxide, we observe peaks corresponding to tetragonal rutile structure of tin for oxide, confirming that we have coated the surface with tin for oxide. and also to determine the surface to be sure that indeed we removed all the silica. We did X-ray photoelectron spectroscopy, and from this you can see for the silica at tin 4 oxide we have oxygen, tin, carbon, and silicon, and for the other one we have no silicon, and the carbon is as a result of the carbon tape used during the analysis. So looking into their narrow X-ray spectrums, we can see the peaks for deconvoluted peaks for silica, for oxygen, for tin, corresponding to tin 4 oxide, and also showing us that we have coated the surface with tin, and this is the spectra for the hollow tin oxide, showing the presence of oxygens with peaks corresponding to adsorbed oxygen and oxygen parentheses. And this one showing the symmetric behavior shows us that we have pure tin oxide on the surface. So with this, we try to look at their sensing behavior, but because it's carbon monoxide, we had to use a different setup, whereby we have the sensor here, the chamber, and we have mass flow reactors. One mass flow reactor is for air, the other mass flow reactor for carbon monoxide, and then to the LCR equipment to get the measurements. So for these one, we really were not successful. We were not successful. We wanted to look into very small ppms, but we couldn't. We only managed to detect carbon monoxide at 10,000 ppm. So that means we could only tell the difference between the template free and the hollow tin oxide. Of course, the hollow tin oxide exhibited 6 times higher response towards 1 volume percent of carbon monoxide as compared to the template free. So these work showed that there is potential, but we need to do more. We need to do more on this. So in conclusion, we can say that hollow tin oxide obtained through the core shell templating approach has the potential for CO sensing, very high COs. That means it must be in a very place with very high CO production. Also, the improvement in the CO gas response in the hollow tin oxide was attributed to the smaller crystallite size and the active sites of the tin 4 oxide brought about by the technique. And the detection of CO under ambient condition, it offers the added advantage because now we don't have to worry about thermosintering that occurs at higher temperatures. And the possibility of using these materials shows this potential to improve it. So probably by looking at the size dynamics or other properties, we can be able to tune these for room temperature detection of other things. So that brings us to why I'm here, which is the carpet print program. We're trying to look into the core shell nanostructures for the detection of volatile organic compounds, trying to do the sensor measurements in a controlled environment, and also to explore the sensing behavior of hollow tin oxide towards the volatile organic compounds. When we did the previous measurements, we did not have a controlled environment in terms of the humidity, so it could be a factor also that contributed to that. So, and also modification of surfaces for enhancing the detection of these pollutants at room temperature in collaboration with Professor Sebena and the group. So we hope to do some great milestones in this area because it will help in the area of research. So these are some of the references I've used in this work, and I'd like to acknowledge all the people involved in this work. Prof. Neil Kondo was my PhD supervisor, Prof. Ivo, Prof. Estiso, Prof. Wamangi, Prof. Toru Sekino in Japan, Prof. Tomoyo, the good group. You can see Professor Sebena here, and the Japanese group, and Capacitors, University of Nairobi, and you all. Muito obrigada.
Thank you for the very nice presentation. I like that picture because I have a long hair. Okay, questions, please. We have time for questions.
Is that sensor aimed towards a specific environment, considering applications? For example, considering traffic, you told us that one of the possible not applications, but
Yeah.
one of the justifications of
Yes.
work is smog and such.
Yeah.
Can you comment a bit on that? What kind of environment you can use these sensors on?
Okay. The ammonia sensors, we actually wanted to use them in a wastewater treatment plant outlet to just monitor the effluent, the ammonia from a wastewater treatment plant, because they generate a lot. But we haven't managed to go further because I relocated back home. Now I have to do things again. Yes. But that was the idea, because to be able to use them in traffic, then that means you have to do selectivity. The sensor must be extremely selective for it to be relevant.
And what's the longevity of the sensor study? In the sense that it degrades fast, or is it stable under a long time period or something like that?
During that time, we didn't look into that, but it's something that I think it's worthwhile to look into moving forward, looking into how long we can do the measurements without losing the efficiency of the sensor. Yeah, it's a very good point.
More questions?
So, let's have some, like a few questions. Do you think it's possible to enhance the size of the hollow carbon spheres, but not just the carbon spheres, but also the hollow monoxide spheres? Do you think we can get some smaller spheres from this? Maybe not just to improve the speed of the centrifuge, but maybe we could go for like something close to quantum dots from this.
Like hollow quantum dots.
Yeah. Not something close to this. Like if we could get some spheres close to 10 nanometers.
I think it's a possibility, because the template you use will determine the final product. So if you have a template that is a very small size, it is possible. But then you have to ensure that it is not agglomerated. It's well distributed, so that when you coat, it coats on one sphere, not on agglomerated spheres. So it is a possibility. It's something that someone can actually look into. But you can't negate the fact that you will need, of course, better techniques for separation for you to be able to get that.
I think this because if you can get a smaller size, you probably will get a way to try to solve the problem of the absorption over the material.
Yeah.
If you're trying to analyze CO, you have all of those sites that are occupied with probably water, and mostly if you're trying to do the ammonia measurements. So the small spheres maybe could fix the problem, but there we come to the second question. Is it possible to use some dopant agent on these materials? Like if you get a crust filled with different metals or metal oxides, like if you do some dopant agents like palladium over the surface of those spheres, it could be a possible solution also, because it forces the interaction between the analyte and the material.
Yeah, that's one of the ways for modifying the surface, the additives, because they help tune the interactions. It's one of the ways. It's very possible, very, very possible. Yeah.
That's something.
And you can use inside and outside, actually. You can do both on the outer surface and the inner surface, which is a very interesting thing. We have done this for catalysis, but for sensing, it has not been explored. I can say that.
We come for the third question. If we can get to use those additives, maybe a possible solution also would be to use those additives to try to obtain a photo excitation for the material, so it could solve the problem of the interaction between the analyte. Because if you're trying to do like the CO measurements, you have to go to a higher and higher concentrations, and maybe with the photo activation of the material, which could get a lower LOD, maybe.
Yeah, that's a
Think that's
possibility.
possible?
Yeah,
Because-
the light sensitization.
Yeah.
That is a possibility. Yeah, especially with the photosensitive materials. Yeah, it's a good thing.
Okay, more questions? I have one. In the sensing mechanism of ammonia, do you need water? I mean, water is part of the sensing, needs to be part of the sensing mechanism, or if you put the devices on an environment without water, you can still measure, sense ammonia? Because sometimes water is a byproduct, or it needs interaction of the VOC with water to separate things and get extra electrons to interact with the material. So I'd like to know this.
When we were using ammonia, we used ammonium hydroxide. So
Ah,
perhaps using ammonia gas, but water should not be like a prerequisite because ammonia gas also is an electron donor. So it shouldn't be a prerequisite, in my view, but it's subject to investigation.
okay. So you can with that system you showed, the two stimulus, you can actually separate the contribution of water and contribution of ammonia, right?
Yes,
But you can do that for other mixtures, right?
yes, you should be able to.
Okay.
Yeah.
For example, acetone and alcohol and things like that.
Yes, as long as there are 3 set of sensors, you should be able to. That shows a linear response in relative to the concentrations. So the response of both sensors must be linear for it to justify the use of the tool.
It's similar to ELOs. Then.
Yes.
Okay. Does anyone have any questions? So let's think again.